Okay, projections. Let's do it. If I bring in my unprojected data here, WGS84, this is a world shapefile, plop it in here, and you might say, well, how is that unprojected? It is on a flat screen, and we can see it, so it must be in some kind of coordinate system. Well, it is in a coordinate system. It's in a geographic coordinate system, which is the two kind of WGS84 and NAD83. Those are the two datums that we use, the two geographic coordinate systems. But it is also projected. It is in a default projection that QGIS gives unprojected data. So if data is unprojected, it says, well, I have to show you the data on a flat screen. So let's just give it this projection, which is Plat Carré. And Plat Carré means that we've got it's equirectangular. So there's 1 degree of longitude for every degree of latitude, and it kind of just throws it down x by y. And you'll notice that the units at the bottom are in degrees. For latitude, the positive is the northern hemisphere, the negative is the southern hemisphere, and for longitude, everything kind of east of the prime meridian is positive, and everything west of the prime meridian is negative. So I hope, as you can remember, you shouldn't try to do area measurements with this, because the units are in degrees, and they really just tell us the location of every single vertex. All the vertices are stored in latitude and longitude. So just because our data came in and it has a projection, even if it's a default projection, it doesn't matter. We can still go and change the projection of the canvas to whatever we want. So if you go up to Project and Project Properties, you'll notice that under, usually it comes up with General here, but under CRS, which means Coordinate Reference System, you can check this box that says Enable on the Fly CRS Transformation. And what do you suppose that means, on the fly? Well, what it means is that the program knows that your data is in one coordinate system, but it's going to allow you, on the fly, to put it in any other coordinate system, or at least visualize it in a different coordinate system, so that the map canvas can see it in a different way. So to do that, let's go ahead and type in Mercator, because that's a fun one. And this is the one that gets everybody all excited. I've used it recently, so it comes up here for me, but for you, it'll be down here. And let's use the world _ Mercator. So if it doesn't show up, you can type in world Mercator like that, and it will come up. And that's the EPSG code, which later we'll care about, but for now we don't. That's if you want to find things online. You can find custom projections that way. Anyway, so world Mercator, we say OK, and it transforms our data into this kind of new projection. And I'm showing you this projection because this is one of the more famous projections. It was developed in the 16th century, actually, for navigation, and at the time it was an amazing kind of insight, because if you draw a straight line on this projection, you get what's called a line of constant bearing. So that means, for instance, let's say you wanted to sail from England to the Caribbean, you could just take your map, draw the line, and you say, okay, west southwest, that's how I want to go, and it would actually get you there. So a line of constant bearing means that if you follow that bearing, you will travel on that line. And it's actually not a straight line, and it's not even always the fastest way there, but rum lines is what they're called. Rum lines were things that you could draw on this projection. Today it gets a lot of flack because it distorts area. The kind of classic critique of this map is that Greenland is 1/14 the size of Africa, but in this particular projection it looks like they're the same size, which is absolutely absurd. But it is a good one to know because it's very frequently used as a world map, and it also is used in all of the Google kind of web maps or Bing maps or Apple maps. It's called the tiled web Mercator. So even though this was kind of getting a lot of abuse because it was distorting area and making kind of the global south look really small and diminished when it shouldn't be, it's still a useful projection because we use it in tiled web Mercator kind of online maps. Okay, one more thing before we move on, and this is a really important thing here, kind of takeaway number 2, is that our units are in meters now. We have our map canvas is in a projected coordinate system, but just because our map canvas is in a projected coordinate system, it does not mean that we have now projected this data. The data are still stored in geographic coordinates. So projected coordinate system on the map canvas does not mean that our data has now been projected. How do I know that this hasn't changed? Well, if I go to my properties and under my general tab here, it says coordinate reference system, EPSG 4326, WGS 84. It would say a different projection name, and you should start to recognize that the projection name will be there, and every projection still has a datum. You have to have a datum, but this only has a datum. That's the difference. A projected coordinate system has kind of the projection along with a datum, but if there is no projection, then you just see the datum. So this this layer here, unprojected WGS 84, is still stored in kind of degrees, even though we're visualizing it in the projection. So how do we change the projection then? We know that this is unprojected, but what if we wanted to project it? Well, then all we have to do is say save as right here. And then in vector, you just save it as a new projection. So you would save the vector layer as the shapefile, find a place on your computer to put it, and then go here and choose your new projection that you want to save it as. If we wanted to make a measurement, we know we can't make measurements with decimal degrees, but we probably, I'm hoping you can see, we shouldn't really save it as a Mercator projection either, because measuring area in this projection is a bad idea, right? So I want to show you two ways that you can two projections, I should say, that you can use to measure regionally and locally. Globally, you want to be careful about making any kind of assertions about measurement, but regionally we can kind of do it. So I'm going to go up here and just say new. I'm just going to kind of wipe the slate clean here, and I'm going to go new, say discard, and I'm going to drag in what says, it says AEA North America, and this is a projection called Albers equal area, and you'll notice that it kind of distorts South America in this case, and that's because the projection is centered on North America. And North America looks pretty good, actually. This is a conic projection, not that you need to know that right now, but it preserves area. And so this is pretty easy to do. You can go up here and type in, let's just do another on the fly, project properties. On the fly, we can change it to South America, and let's see what that looks like. I'm going to go Albers equal area, and you get all these options. Let's say South America, Albers equal area conic, and we click this, we say OK, and now South America is kind of the focus, and it's centered on that, and North America is wildly distorted here in terms of its shape. Again, area should technically still be true. The area of the United States should not have changed, but I would always try to center the projection on the place you want to make the measurement. And so I've included a couple here you can play around with. And just because I've changed, it to South America, my data is still the Albers equal area that's centered on North America. Okay, I'm going to throw just one more thing at you to saturate your brain. And just like how with the Albers equal area conic projection, you kind of have to choose where you're going to center it. So with that one, you had to choose North America, South America, Europe, Africa, that kind of thing. There's a way of choosing projections called the Universal Transverse Mercator system. And this is for kind of mapping local areas. I'm not going to get into all the details, but it uses a transverse Mercator projection to strip the world into these zones. And if you're ever completely mapping within just one of those zones, for instance, if you're mapping Maine, you can say, well, I'm in the UTM zone 19, and it's 19 north actually, there's 19 north and south, and you say, I'm in zone 19 north, I'll use the UTM 19 north projection. So it's a whole series of projections, but the reason it's useful is that you can kind of just say whatever zone you're in and then just grab that projection, and it does a great job of kind of mapping that part of the world. For instance, Maine, if you can look at Maine here, it's in UTM zone 19 north, and here it is projected in UTM zone 19 north in that custom projection. But you'll notice when I back out, the rest of the world kind of gets bent around that one strip. So it's good for that strip, but not good for mapping anything else really. So thank you for making it through this kind of nauseating video. There's a lot to learn. I'm going to do a quick recap right now, and if you come back in the future, just look at this recap. It's tagged in the information on YouTube. And the recap is going to show you the 4 projections I want you to care about and give you 3 pointers for dealing with projections in QGIS. So first, the 4 projections I want you to care about and learn are the Plat-Carré, and Plat-Carré is the projection that is the default projection for unprojected data. The Mercator projection, and this was kind of the historical projection used for navigation, but it's still used today for many purposes, one of which is web maps. This is the Albers equal area conic, and this one needs to be centered on the area that you want to measure. It's good for regional measurement of area. And here it is centered on South America instead of North America. Here it is centered on Europe. And here are all of the UTM zones, and it's shown in a Plat-Carré projection right now, but it's a way of finding a good custom projection for each individual zone if you want to map kind of at a local scale. The 3 things I want you to remember about projections moving forward are that the first file you drag into your workspace is going to define the workspace's projection. If you bring in unprojected data, the default projection will be Plat-Carré. So the first thing is whatever you drag into your map canvas defines the map canvas's projection. The second thing is that you can have multiple coordinate systems all reprojecting on the fly, and all of these different systems right now, I hope you can see I've got 3 pieces of data: my unprojected WGS 84 data, my Albers equal area North America data, and my UTM 19 North Maine data. And these all have separate coordinate systems, but are all being shown together in the map canvas area because they're being reprojected on the fly. Maine is in 19 North. This one is in the Albers equal area centered on North America, and this is unprojected. Each of these pieces of data has a different projection, but I dragged in this one first, and that's why it's all, the map canvas is showing it all in that one projection. The third and final thing is that if you want to actually change the projection of one of your shapefiles, you have to save it as a new file and change the coordinate system when you do that. Even though this file is being shown in a projected coordinate system, the data themselves are not stored in this projection. They're stored in the projection that they have, and you need to save it as a new file if you want to make measurements with it and alter that file so that it is projected in the proper system. So that's a lot. Good luck. We're only going to reinforce this as we go on, and hopefully if you made it through this video, you will definitely make it through the ones to come.